everybody, and welcome to Nuking Nasty Memory Leaks. So my name is PY. I work at Square. I'm part of the API team, so I'm not going to talk about that. So we have a huge attendance today. There are no cameras, so I can say whatever I want, and the recording is going to sound like... can you actually cheer a little bit, like clap? Yeah, woo! See, so many people. All right. So who has made an Android app before? I think about 100 people just raised their hands. So how many people have dealt with out-of-memory errors before? Yeah, that's 200 people. So at Square, we've been through the same issues. And we realized that there are sort of two reasons for out-of-memory errors. One of the big ones is just that you're trying to create something too big. That's never the case. The second one, and the real reason, is memory leaks. And so LeakCanary is a library that helps you detect memory leaks in your dev environments. So we made this library and started working on reducing memory leaks. And when I say we, I really mean I. But I'm not trying to put myself forward. What I mean is that I kind of got the hang of it and started fixing things. And then I was like, then I stopped, and then the number of crashes went up again. And I realized that I was the only one doing it because it's really hard, and I worked with intuition, and I wasn't really good at explaining how to actually understand those things and fix them. So I sat down with a couple engineers, and we did it a few times, and then we came up with sort of a method, and this is what this talk is about. So let's pretend that we're new to Android. We haven't really done any Android before. And we want to make an amazing app. We love the color blue. And we want to make an app that's blue when it's focused, and that's not blue when it's not focused. And we're going to use multi-window because why not? So here we have an app, and it's split into a multi-window. And then it's not focused, it's gray. It's focused, it's blue. Oh, that's amazing. A really fantastic app. So we release it. We get 1 million downloads. I love huge numbers, as you can see. So we get that 1 million downloads, and everything's going great until we get a lot of one-star reviews because the app is crashing. So we start looking at the crash reports, and the crash reports, they say, you got an out-of-memory error that's happening a lot. So what do? Well, there's a check mark there that says marked as fixed. So you try that first. It doesn't work. It comes back, and people are still unhappy. So then I talked to my friend, and he tells me there's a library called LeakCanary. You should try it out. So it's actually pretty simple. You essentially add a bunch of dependencies. There's this application class that's a singleton in Android, and you just have to extend it and add like a few lines of code. And then apparently that works. And so now we look at, we run the app again. We're in dev. And all of a sudden, there's going to be this like huge freeze of the UI and a little toast that pops up. And the memory, a heap dump has been taken. The memory is dumped to a file, and then analysis runs. And then you see a notification that tells you, hey, we found a leak. And so we click on that notification, and we get to this. It's super fancy. It looks cool, but not really sure what to do about it. It's called a leak trace. And so if I look at it the first time, I'm like, I don't know what any of this is, except I see at the bottom there's a class called NeoMob Realism View, and it's a custom view that I wrote. So I'm going to look at it. I'm like, OK, cool. What's this view? Well, it's a view that sets a background color in its constructor, and then it does something amazing, which is it registers an activity lifecycle callback when it's attached to the window, and it changes the alpha from 1 to 0 and 0 to 1 when the activity is paused and resumed, i.e. when the app is focused or not. So that's what you saw here. The view is focused and unfocused, and the color changes. So that's cool. If you're an Android developer, you have seen this. You immediately saw that something's wrong. The application is a singleton, and when you register an activity lifecycle callback, you register it on a singleton, so it's going to stay there forever. And if you never unregister it, well, your singleton is going to, the callback is going to leak, and you're leaking your view hierarchy, and everything's bad. So the solution seems pretty simple. We're going to extract that callback and then remove it on the attach from window everybody's happy, problem solved. So that's what I used to do. The problem is problem solve, not really. How did we fix this problem? We used intuition. We saw something wrong, and we fixed it. And that's the Crashlytics stamp. Problem fixed, no problem anymore. So the problem is, this was a very easy thing, and I just poked around, found a class, found a leak, and I fixed it. But I actually have no idea how I got there. Like really good, like people who are good at fixing, say, performance problems, for example, will tell you that you never start with the code. You start from the out, and you start observing, and then you dig, and only then. So that's what we're going to do. So let's take a step back, and let's learn Java again. We're going to start with the Roomba, the garbage collector, and the principles of, very basic principles of a garbage collection. So we have 3 classes, class A, class B, and class C. And then we have a method in which we create a new instance of class A, right? So what happens when the method is called, an instance of A is created, and then it's garbage collected. Everything's great. OK, we're going to do the same thing again, but create 3 instances. And we are going to create references between those classes, right? And then we're going to set those references so that every class depends on the other, right? So we have an island. So what happens when we call the method? Well, same thing. The whole group of class, the 3 instances are garbage collected. Everything's fine. Now we create a static field. And we have that static field reference one instance. And then we call the method. Now what happens? No garbage collection, because the whole graph of object is held by the static field, right? So this static field is called a GC root. And the reference is never cleared. Other types of GC roots are local variables on threads that are running or native code. So if you zoom out, you essentially, in your Java memory, in your Java heap, you have a bunch of GC roots. And they hold 2 objects, which hold 2 objects. And that's essentially a graph, right? A direct graph. And you have some isolated groups of isolated objects, islands, like this one in the middle. And these can be garbage collected. All right, so now we know that an object that's connected to a GC root cannot be garbage collected. So let's look at this and say this is one activity. And this activity here has been destroyed. And destroyed is a lifecycle event in the Android lifecycle. That means that the activity is not going to be used anymore. It should be garbage collected soon. And here we can see that it cannot be because it's connected to a GC root. So we have that activity. It has an mDestroyed field that's set to true. So it's clearly leaking. And the problem is the activity references a bunch of views which have bitmaps. So there's a whole world of things that are kept in memory because that activity is leaking. So what's going on here? The activity is leaking because it's connected to the GC roots. And we can draw the paths from all of the GC roots to that activity. And there is not one path. There are multiple paths. And actually, in real life, you can have hundreds of paths and combinations of paths from any number of GC root to one instance. And if we want to fix the GC root, what we really need to fix the leak, what we really need to do is find the connections that need to go. And it turns out that we don't need to find many connections. We actually just need to find one, the one on the shortest path. Because there can be many leaks, but if you fix one leak, then that's one less problem, and then it's going to come up again, and you'll find another leak. So all you need to do is look at the shortest path, which here is that one, and then find the wrong reference. And that's exactly what LeakCanary is doing. So what happens with LeakCanary is that it will perform a heap dump, and then process the heap dump, find the shortest path to a reference, and then show that to an object, and show that in the UI. So this and that are exactly the same, these two things. In white, you see, in LeakCanary, you see the nodes, and in purple, the fields are actually the edges. All right, so let's come back to this. So we have shortest path to, so we're seeing our shortest path, and one of these connections shouldn't exist. And let's pretend that we already know that, in fact, the 2 green instances at the top are objects that should be alive, for example, singletons. And the 2 red at the bottom should be garbage collected at this point, right? And so it's very clear at that point that the problem is the the connection between the green to the red. And so if we break it, then the whole thing is isolated and can be garbage collected. All right, so this is all nice, but how does that translate concretely? So on mobile devices, generally, you actually have on your Android devices a lot of memory leaks. That's just how it is. That's life. And these are small, and they're not generally a problem, except that they accumulate over time, and that makes the app crash. So let's apply the method that we just saw to a real concrete example. So we have this leak trace, and we started. The way we started was find a view and look at it. So if you know Java a little bit, you know that an anonymous class is actually compiled to a distinct class that keeps a reference to the outer class. So this is what it looks. And the class is named $1, outer class $1. So when we look here, we can actually split the whole leak trace in two areas. The top is the objects that are alive and should be alive, and the bottom is the objects that should not be alive anymore. And this is the link that we need to kill. But how did we figure that out if we don't use intuition? Well, what we actually do is we can look at every single object there and make a decision. Say, should this be dead? For example, the activity is leaking. That I know for sure. It's destroyed. So it's red. The application class is a singleton. It's green. At that point, every time we make that type of decision, we know that everything above a green object is green, and everything below a red object is red. So it becomes very easy to move forward and make decisions. For example, the view. Well, what about the view? The view that's right there at the bottom. We can actually, so LeakCanary provides a string output with some, it's not like a full, it doesn't provide the full state of everything, but it provides the fields of every object on the leak trace. So if we scroll down, we can see that, I'm going to get there, that there is, the m attached info is null on the view. What does that mean? Well, if you look at the Android code, you'll see that the view class has an m attached info field and an is attached to window method that returns true if m attached info is null, is not null. So what that means is that if this is null, as we saw, then the view is detached, which means it generally should be garbage collected, in that context at least, and therefore we can realize that, OK, so these objects should be gone. And now we can look at the top and see that it's an array list, and then below it is the implementation, the array. The array list is the list of listeners in the application, so that list itself should stick in memory. What should not have been in memory is the listener itself. So we're back to where we were. OK, let's actually start to get a little bit more. So this was an easy example, right? We're going to look at two examples, one from the support library and another one from Square's code. But before that, so LeakCanary gives you a notification that tells you, hey, I found a leak in your dev application. What do most people do, most developers? They don't sit down and fix it. They just swipe out the notification and move forward because you have a lot of work to do and you don't have time to deal with that. So that's not great. So what we did instead is we thought, well, we should capture all the things and send them to a backend. I haven't done server in 6 years, and I'm lazy, so I didn't want to do a backend. So instead, I realized that we have crash reporting tools. So I made a fake stack trace, because you can do that in Java. You can create fake stack traces based on, because it's very similar, based on the leak traces, and then just upload them to a crash reporting tool. And it looks like this. It looks like a stack trace, but it's not actually a stack trace. The fun part is that you benefit from the grouping and counting that these tools usually provide. And that gives you, that way you can actually fix the most important memory leaks. And then you can look at a better representation of that. And we can reapply the same thing. So let's look at this one. For example, here at the root, we can see that there is a main thread enforcer that has a field that's called main looper that references a looper. That's the main thread looper. It should stick around. We're pretty sure about that. It should not go away. Everything's fine. On the same, we can also look at the activity. The activity is at the end. That's what LeakCanary found. We know that it's leaking. Now, let's look in the middle. OK, this is getting interesting. The run queue. this is an Android class. So people's reaction to that might be, oh, this is Android, not my fault, I don't know, I don't want to touch it. But we can actually, Android is open source, we can actually go and look. So what is the view root impl run queue? OK, let's figure this out. It's an inner class of view root impl, and it has a couple interesting methods. One of them is post delayed. You pass it a runnable, it wraps it, and then puts that in an array list that is stored in the run queue. There's also a post method that just posts with a delay of 0. The question is OK, we're putting into a queue, when are we dequeuing? Also, we look at Javadoc, and Javadoc says that the work is executed during the next call to perform traversals on the thread. So the queue is going to be dequeued the next time there's a traversal. And also says that the run queue is used to enqueue pending work from views when the no handler is attached. So let's check that out. Let's look at the view class. And we can look at post and post animation. So in the view class, you can post work to execute later on the main thread. And the implementation is pretty simple. There's, again, this mattachinfo field. And if the view is attached, just post to either the choreographer or the main thread handler, or put it in a queue to be executed later on the next traversal. OK, that's cool. What does viewRootImpl.getRunQueue do? Well, the implementation is, again, relatively simple. There's a static field. It's a thread local because there's only one run queue per thread. Usually, that's only the main thread. But some people do UI not on the main thread, I guess. And so that thread local keeps a variable for each thread. And then then it's pretty simple, right? It's like, do I have a queue? Yes, return it. Otherwise, create it and put it back in there. So if we come back to our leak trace here, and we look at these two elements over there, it mentions thread locals and so things that we're not very familiar with, but we just saw that there was a thread local. So that's pretty much essentially the static field that's holding onto the queues. And then we can see that this is the queue, right? And so if we think about it, OK, there's a thread local holding onto a queue. The queue should stick around, right? It's static, and it's going to be there forever. So we can make the decision that it should stick around. It's green. And we can expand our green area. And similarly, we can look at the list of action, right? So there's an maction field that's referencing an array list that has a backing array. And the first element of that backing array points to the next object, the action. Well, that list is essentially what's in the queue. Should also be around. That's pretty easy. Now we get into the more intriguing part. What is this app-compat delegate impl v23? It's an instance of app-compat delegates. And if we look at the code, we see that there's something called app-compat activity. And essentially, it's a companion, a delegate that lives in there and that receives all the callback and deals with that. So if you think about lifecycle, that means that when the activity is destroyed, the delegate should be destroyed as well. It's created for the activity, and it should go away with it. So if the activity is supposed to be destroyed at this point, the delegate should not be around anymore. Now we can look one row up, and we see that there is an anonymous class in the v9 version of that class. So essentially, there's a hierarchy of classes, v9, v23, that override each other. And so there's something that's referencing that. And so if we look at the code, we actually see that there's a runnable that's invalidate panel menu runnable. And it's apparently leaking. So where is it used? It's used in invalidate panel menu. And it posts on a window decor, which is a view. It posts that runnable. So if we wrap it up thinking about what we just saw, we're posting an animation to a view. And we saw that if the view is not attached, then the post is done on it's just stored on the run queue and will be dequeued later. It will be dequeued on the next traversal. Now the problem is what happens if the activity finishes and there is no next traversal because there is no next activity for now. The thing is going to stay in the queue until there is a next activity, which might not happen for a while. So the fix should be relatively simple, which is in whatever that delegate is. Just when the activity is destroyed, remove the callback from the view, and that will clear it from the queue. So that's something that we filed on Android. I haven't checked in a while. I think they eventually fixed it, I hope. I think they did. the screenshot is old. So that shows that whenever you have a leak, it doesn't mean, and even if it seems to be in Android land, it doesn't mean that you can't do anything about it. You can actually report it, you can provide a fix, and in 5 years, it's going to be fixed on your phone. So that's pretty great. Sorry, I had to. So let's look at something that was a little bit harder for us in the Square code base. So we got another leak. And in there, there's a view. I'm like, oh, I know this view, passcode unlock view. It's one of our things. So I know how to check if a view should be garbage collected or not, right? So I just go into the details of the state and look for a field called element attach info. Oh, it's null. The view is garbage collected. I know in that context it should be gone, which helps me a lot because now I don't have to look at anything at the bottom. I know all of that should be garbage collected. Then I see an anonymous class. Actually, it's an anonymous class in an anonymous class, right? So it's $4, $1. What is it? So I look at the code, and it is just, there's a set background image that takes a request. That's a Picasso request. Picasso is our image library. It loads pictures, and it makes that very easy. And so instead of just showing the picture, what it does is wait for the view to be measured, to have a size, and then start this callback that's going to download the image at the right size. The point of this is basically we want to wait to have a view that's measured, and then we're going to ask the server for an image of the right size, and then we're going to insert it. So, OK, that's cool. And we can see that this is what's happening there. We start the Picasso request, and we provide an image view, and it's going to call back into it and set it when the image is there. So let's look at request.into_javadoc, because Picasso is a really good Square library, and it has really good Javadoc. And as we see, it says asynchronously fulfills the request into the specified image view and invokes the callback. Note, callback is a strong reference and will prevent your activity or fragments from being garbage collected. Oh, it kind of rings a bell, just what happened. If you use this method, it is strongly recommended you invoke cancel request to prevent temporary leaking. All right, so open up passcode unlock view. Cancel request was already there. It was doing the right thing. So that's kind of weird. What do I do now? So we start looking at the cancel request implementation, and we can see that it's pretty simple. It has a map of targets to actions, and it removes the target, gets the action, and calls cancel on it. And if you look at an action has a cancel field. That's interesting because that action is on the path of on the leaking path. So if we can actually see it, and we can see that it was not canceled. So now it's weird. We do a call, and on the attached to window we actually cancel, but it's not canceled. Something is clearly not easy to understand. Something is wrong. So if we come back to the leak trace, we see that the action should not be around. But the list of action that's right above should be around. It's pretty easy to do that distinction. And now we have a problem. We've actually done our job of investigating the leak trace and finding the top part that's what should be around, and the bottom part that's what should not be around. And we're doing the right thing. We're calling the code, and we're still not able to understand what's going on. So that's when you actually have to pull out the real tools. So memory analysis, or anything that's a heap dump parser where you can poke around. So we needed heap dumps, which means you're using things, and usually it happens later. We look at the thing that's happening the most. So it's always async. So we needed to upload heap dumps to a backend in background automatically so that we can then download them later. But I'm lazy. I don't want to build a backend. So I found a better solution. It's called Slack. Slack has an API, and you can call into Slack API and upload whatever you want. So we created a channel on our Slack, and it's a bot channel, and it just gets all of the heap dumps uploaded to Slack, and then we can go later and download them. And I'm still waiting for someone at Slack to call us and tell us to not do that, but so far it's been working great. I can't imagine how much data that represents. I don't actually want to know. It's actually very interesting. Trying to open it on Slack just freezes your instance for quite a bit. It's really nice. So let's open this in Math and figure out what's going on. So if we come back to this, we saw that Picasso has this target to action field. So let's look at it. Let's find it in Math. Math being memory analysis tool. So we look for Picasso. We notice that there are two instances in memory. You can see on the far right side. And it has a target to action field. The first instance has a target to action field that is a hash map with a size of 0. Doesn't seem to be what we want. And the second one has a size of 1, and it has our Picasso image view action in it. We found it, OK. But that doesn't really mean that we found the leak. We just, yeah, as expected, it hasn't been canceled. It's still in the map. So how can it be canceled and still in the map and not removed, but we are calling cancel request from unattached to window? Like, what's going on here? So there's a Picasso field in that object. So let's look at that Picasso field in Math, right? So we open the passcode unlock view, and we open up Picasso. And that's where the surprise is, because we open up that Picasso instance, and we see size 0. And now it starts to click. There are two Picasso instances. My view has the Picasso instance with size 0. But there is another Picasso instance that has the anonymous class that we were dealing with. So what's going on exactly? Well, what actually happens is that the Picasso instance was injected by dependency injection. And so we can probably blame dependency injection for that. But what's actually going on is that when we call set background image, we pass in a request, and that request actually has a reference to another Picasso instance. And so we're canceling the request on the wrong Picasso instance. So we just had to unregister from the right Picasso instance. So with that said, that was a quick introduction to LeakCanary. The key principles are try to not use intuition. I tried to remove myself more and more from intuition and trying to not jump to the code directly, but just apply this like green, red method and avoid jumping to conclusions. And you just need to find which ones should be around, which ones should not. And if it's below, if you find something that should not be around, everything below it should not be around as well. It's a bit of an oversimplification, but it works 99% of the time. And that way, you can find the reference that's wrong. And most of the time, you actually fix the bug that way. And sometimes, you actually need the heap dump to figure out how to fix it. With that said, well, I think that's it. I'm done. Thank you. Oh, and a word from my employer. We are building APIs, and we would love to have more people using our APIs if you're interested in taking payments, which has nothing to do with memory leaks, but is super interesting in itself. I suggest you go to Square APIs. And Jake, who does not work at Square at all, has a question. Yeah, so the question, that's a really good question. The question is, can the machine do the work for us? And can we be more lazy even? Yes, we can. If someone wants to contribute to the LeakCanary projects and implement that, it's actually, I have a branch from a long time ago that does that. We could really automate we could basically use pattern matching for views, activities, fragments, and a bunch of classes that we know we have easy ways to detect whether they should be around or not. We could totally do that and just simplify and just really show you where the bug is. I think that's a very reasonable ask, and I wish I had more time to do that. Yeah.
In the demo, you showed that at a certain point and a certain time you clicked on the window and then a heap dump was generated. But that was automatic because the application the library already detected the leak, or it was just dumping and then the library.
It's a really good question. So I didn't go into the details of the runtime of LeakCanary. The question is, how do you get the heap dump? Was that automatic, or like how does that work? So LeakCanary is actually a very simple implementation where what you need is objects that have a life cycle, and when you know that there should be garbage collected soon, you trigger something. So what we do is, so activities, for example, have an onDestroy callback. In onDestroy, we put the activity reference into a weak reference, and then we use a, what is it, queue? Oh, forgot the name. Anyway, basically 5 seconds later, we check that weak reference, and if the weak reference is cleared, then there's no leak. The object has been garbage collected. If it's not cleared, well, we do the usual. We do system.gc, wait a bit, system.gc, wait a bit, just to make sure that, and then we check again. And if it's still not garbage collected, then we assume that there is likely to be a leak. And then Android supports, there's a static method in Android to actually dump the memory. So you just call debug. I think it's heap dump or something, dump the heap or whatever, and push it into a file. And then we spin off a new process, and we start parsing that. When I say we, I never wrote that code. It turns out that originally someone made a fork of mat with no UI. So that's what I used. I just packaged it. And then recently, the Android team actually made a new heap dump parser for Android Studio that's also based on the same original source. I think that was JHat. And I used that instead. And then it's just navigating through a graph, finding the shortest path, and that's all provided. So it's all automatic. Say you're writing server applications, you don't have the automatic heap dump. You have to do some external integrations probably to do that. And I also don't know that on servers you have the same easy objects with a clear life cycle that tend to leak often. One of the key reasons that this works so well on Android is because activities are God objects. They are able to do everything. They represent a lot of things, and they hold on to a lot of memory, and they have a life cycle. So they're perfect candidates for objects to track that should be garbage collected. And if you have a similar context, then it works well. If you don't, then maybe it works less.
Yeah, it looks like something Android itself.
If there were people working at Google in this room, maybe you could talk to them. But I don't think there are. Just kidding. All right, I think we need to leave room for the next person. Thank you.